So welcome back to the class. We're up to lecture 6, and today we're going to talk about backpropagation. So where we are in this class is that now last time we talked about neural networks, and we saw that neural networks were this very powerful category of classifiers that let us do a lot more powerful computation than had been possible with the linear classifiers that we had been considering so far. You'll recall that neural networks had this fairly simple functional form of a matrix multiply, this element-wise nonlinearity that we called an activation function, together with another matrix multiply, and then we could chain these things together to get really deep neural networks. And we saw this notion of space warping to recall that, to demonstrate one way in which neural networks were much more powerful than linear classifiers, where neural networks are now able to have these nonlinear decision boundaries through the input space. And we also talked about neural networks as a universal approximator to give another notion in which neural networks are a very powerful class of functions. We also saw this notion of non-convexity, that neural networks, despite their very powerful ability to represent many functions, resulted in non-convex optimization problems that have very few theoretical guarantees. And now we were kind of left with a bit of a problem here at the end of the last lecture, which is that now we have the ability to write down these very complicated expressions that describe loss functions that we want to minimize using stochastic gradient descent in order to train our classifiers, be they neural networks or linear classifiers or other types of deep learning models. The problem here is how do we actually go about computing gradients in these models? We know that we can write down arbitrary loss functions, and if we can find some way to compute the gradient of the loss with respect to all the weight matrices of the model, then we know that we can use the optimization algorithms we talked about a few lectures ago in order to actually minimize the loss and find good models that fit our training data. And the topic of today's lecture is how do we actually go about computing these gradients, these derivatives, for arbitrarily complex types of neural networks or other types of functions. The first strategy that you might be familiar with, that you might try to adopt if you just attack this problem naively, is to just derive the gradients on paper, right? You know that we can write down these functions, these loss functions, and expand out the loss function on paper as an equation with many terms. And here I've expanded out the SVM, I think this is an SVM loss function with a linear classifier. And one strategy you might go about doing this is you just write it all down on paper, you expand out all the terms, and you end up with a giant equation that represents the loss as a function of your data and the weights of your model. And then if you're very familiar with the rules of matrix calculus, you could imagine trying to churn through this and just compute expressions on paper for all of the learnable weight matrices that appear in the model. This turns out to not be a very scalable solution. So I apologize if anyone actually attempted this for the second assignment. If you did go this route and try to compute these weight matrices on paper for the second assignment, you will have noticed some of the potential shortcomings of this approach. One is that it's extremely tedious. You probably needed quite a lot of paper to get this thing right as you were working with loss functions like the cross-entropy loss function or the SVM loss. Another problem is that it's not very feasible for complex models. For something like a linear model, I think you can probably get by with this approach. But as we scale to much more complex models, this approach of writing down gradients and deriving them on paper will just not scale to more complex models. And a final, somewhat subtle problem with deriving everything on paper is that it does not lead to a modular design. Now, suppose that once you've derived your loss function for a linear classifier with an SVM loss, and now tomorrow you want to derive the gradients for a linear classifier with a softmax loss, or a 2-layer neural network with a softmax loss, or a 5-layer neural network with an SVM loss, or any other kind of combination of losses and architectures and regularizers that you might imagine. If you were deriving these things on scratch, on paper, for every combination of loss function and architecture, you would have to rederive everything from scratch every time. And in practical situations, it's much nicer to have some modular approach, where you can just swap in and slot out different types of models and architectures and loss functions. That will allow you to iterate much more quickly as you try to find models that work well for your data. The approach that we tend to take in deep learning is actually, as you may have guessed, not deriving gradients on paper. And since we're computer scientists, we like to try to find data structures and algorithms that can help us solve tedious problems. And the data structure that we use to help us solve this problem of computing gradients is called a computational graph. Now, a computational graph is a directed graph that represents the computation we were performing inside our model. And here on the left, we can see the inputs to the model the data x and the labels y, maybe, not in this graph, but maybe here we have the data x and the learnable weights w coming in as nodes on the left of the graph. And now as we proceed through the right, as we proceed from left to right in this graph, we see nodes that represent bits of fundamental computation that we want to perform in the process of computing this function. So we see that there's this blue node that represents the matrix multiplication between the input x and the weight matrix w. We have this red node that represents our hinge loss if we're using an SVM classifier. We have this green node that represents the regularization term in our model. We have a sum that represents the sum of the data loss and the regularization loss. And then finally, on the right, we have the output of the computational graph, which is the scalar loss L that we want to compute when training our model. Now, this computational graph formalism, when applied to something like a linear model, might seem a little bit silly and a little bit trivial. Because in a linear model, as we said, there's only a couple operations that we need to perform in order to compute the loss. And the formalism of writing them down as a graph might seem a little bit of overkill. But this will become critical as we move to more complex and larger models. For example, something like AlexNet is a deep convolutional neural network with 7 convolutional layers and a nonlinearity and regularizers at every layers and a loss function at the end, where now the images are coming in at the top and it's going through many, many layers of processing, and our final scalar loss is coming out at the bottom. And something like this, you probably do not want to derive the gradients on paper. Instead, you really want to use this computational graph formalism to track the data structure, to build up a data structure that represents all of the computation that the model will perform in order to compute the loss. These things can get arbitrarily crazy. So here's an example of a model called a neural Turing machine. If you remember your intro of theory to computation class, you remember that a Turing machine is this formalized model of computation. Well, it turns a couple years ago, some folks wrote a neural network that is kind of like a soft differentiable approximation to the Turing machines that you learn in this intro to computation class. And here on the screen, we're showing the computational graph that arises from this differentiable neural Turing machine. And you can see that it's very big and complex. And you definitely don't want to compute gradients in this model by hand. You really want to rely on the computational graph formalism to compute gradients for you. But actually, it gets even worse than this, because with the neural Turing machine, this is showing only one time step of the model. And in practice, this model gets unrolled over many time steps as a kind of recurrent network. So you can see that once you get into these very complex models, you very quickly get computational graphs that are much, much too large to even fit on a slide. So you definitely want to use some kind of graph traversal algorithms to help us automatically compute gradients for us on top of this computational graph structure. Hopefully this has properly motivated why it's really going to be really critical for us to use computational graphs in order to compute gradients in our big complex neural network models. Now that we've got this motivation, let's actually see a concrete example of how we can use a computational graph to help us compute gradients in a little tiny neural network model. Here, in order to actually fit an example on a slide, we're having to use a very trivial computation. But as you've seen, in real models, we'll be doing much more complicated processing. Here we're showing a very simple function of 3 scalar variables, x, y, and z, that simply, the output is now we're going to add x and y, and then multiply by z to compute the loss. This is maybe a weird loss function, a weird learning problem that doesn't make sense, but hopefully this simple example will help us walk through exactly what it means to compute gradients in a computational graph. Well, when we're using and by the way, this backpropagation is this algorithm that we use for computing gradients in a computational graph. Now, suppose that we want to evaluate this function at a particular point in the input space. Say x is -2, y is 5, and z is -4. Now, the first step in using this computational graph is called the forward pass. In the forward pass, we'll proceed in computation from left to right, and we will perform all of the operations specified by the nodes of the graph in order to compute the output values from the input values. So in this example, we'll simply add x and y, and we'll get this intermediate that we're going to give the name of q. And then to compute the final output value f, we're going to multiply q by the input value z. And by running the forward pass of this graph, we'll end up computing our final output value of -12 in this case. Now, in the backward pass, our goal is to compute all of the gradients of the derivatives of the derivative of the output with respect to each of the inputs. So in this case, our output was f, so we want to compute the derivatives df dx, df dy, and df dz. which are the three inputs that appear on the left side of the graph. And we'll proceed from left to right because this is backpropagation, so it needs to proceed backward compared to the forward pass. We always start with the base case. So in the base case, on the right, we want to compute the derivative of f with respect to f. Anyone got an idea what that ought to be? Yeah, that's trivial. That's 1, because if we change 1 a little bit, if we change f a little bit, then f is going to change by the same amount, so the derivative is 1. And when we're computing, by the way, when we're computing derivatives or using backpropagation in a graph, we'll often write a little diagram like this, where we show the values that are computed at each node above the corresponding line, and then we'll write down the gradients or the derivatives below the corresponding line during the backward pass. So now the second step is we want to compute the derivative of f with respect to z. And in order to do this, we know we can look at this little intermediate computation. We know that f was q times z. So we know that the derivative of f with respect to z should just be q. And then we can go back and look into the computational graph and look up what the value of q was. In this case, it was 3. So now the derivative of f with respect to z in this little piece of the graph is now going to be 3. And now we've got one of our 3 gradients that we needed to compute. The next piece, we need to compute the derivative of f with respect to q. You can see that we're kind of marching backward in an opposite topologically sorted version of the graph. And in order to compute the derivative of f with respect to q, we again know that f is qz, so this local derivative should be z. We can look up the value of z from the forward pass of the graph and compute the derivative as -4. We can continue proceeding to the left. Now we want to compute the derivative of f with respect to y. And here things get a little bit interesting, because now we need to remember the chain rule from calculus. Because here, the value y is not directly connected to the output value f. So in order to compute the derivative of f with respect to y, we need to take into account the influence of y on the intermediate variable q. So then the single variable chain rule from calculus tells us that df dy is equal to dq dy times df dq. And this is very intuitive, right? The idea is that if y changes by a little bit, then q is going to change by some little bit dq dy. And then if q changes, then f is going to change some little bit, which is the other derivative. So then to take into account these two effects, we need to multiply them. And now here, in this case, we know, now in the context of neural networks, these 3 different terms in this equation have particular names that we'll use over and over again. So this left-hand term, df dy, we'll often call the downstream gradient, because this is the value of the derivative that we're computing at this step in the process. This value dq dy is going to be called the local gradient, because this is the local effect of how much this value of y affects this next intermediate output q. And this value df dy is going to be called the upstream gradient, because this is the effect because now we're kind of imagining zooming in on this little piece of the graph around y, and the upstream gradient tells us how much does the output of this piece of the graph affect the final output at the very end of the graph. So that piece is going to be called the upstream gradient. And then, of course, the chain rule tells us that to get the downstream gradient, we just need to multiply this local and upstream derivatives. And then, of course, here we know that the local gradient in this case, we know that q is equal to x plus y. So the local gradient, or local derivative in this case, is just 1. So when we multiply these two together, we know that the derivative of f with respect to y is the same as the derivative of f with respect to q. So we get our downstream gradient of -4. Was that clear to everyone? Okay, good. And now it's very similar when we want to compute this other thing. We, again, need to multiply the upstream and local gradients. Again, the local gradient is 1 because this was a simple addition, and we compute our final output value. So here you can see in this relatively simple example how we can use computational graphs to help us mechanize the process of computing derivatives in very complex functions. During the forward pass, we're going to compute everything from left to right, and then in the backwards pass, we're going to step backwards backwards through the graph, and then compute these little derivatives at every point in the graph. Now, this way of thinking about computing gradients is very useful because it's modular. And now, one way to think about it is we can zoom in on one little node inside this computational graph. And what's really great about this mechanism for using backpropagation to compute gradients is that each little piece of the graph does not need to know or care about the rest of the graph. We can just perform local processing within each node, And then by aggregating all this local processing, we can end up computing these global derivatives throughout the entire graph. Now, if we kind of step through this exact same process that we talked about in the previous slide, but in the context of a single local node, it looks something like this. For each node in the graph, we're computing some little local function f. This local function f takes two inputs x and y, and now during the forward pass, we'll apply the local function to compute the local output z. Now that's the forward operation of this little independent node. After the forward operation of this node runs, this output z will be passed off to some other part of the graph. And that might be reused by other nodes in arbitrary complex ways. We don't know, we don't care from the perspective of this one node. We just know that we computed an output and we passed it on to someone else. Then, at the end of the process, eventually, somehow, at the end of the graph, someone far away from us will compute some final loss L. And then backpropagation will start, and somewhere outside of us will just pass these gradients back to us outside of the purview of this little node. And eventually, this backpropagation process will hit this one node that we care about. And this one node will receive a message from upstream in the graph, which tells us the derivative of the loss with respect to z. That is, how much this loss, which may be very far away from this node, somehow we're going to be told how much will this very far away loss change if we change the local output of our node by a little bit. And that's exactly what this upstream gradient, dl dz, tells us. Now at this point, we can compute the local gradients that are internal to this node, which tell us for each output of the node, how much is each output of the node affected by each input of the node, because these local gradients. And now this node can simply compute the downstream gradients by multiplying the local gradients and the upstream gradients. And now these downstream gradients then get passed along to other nodes backwards in the graph that are somehow, again, this node doesn't need to know or care exactly how those downstream gradients will be used elsewhere in the graph. They're simply used somewhere. And by the end, when this final backpropagation process terminates, we'll be left with having computed the gradients of the loss with respect to all of the original inputs of the graph. And we were able to compute this global property without really reasoning at all about the global structure of the function we were trying to compute. It only required us to think about locally what's going on inside each node of the graph, and then have some data structure to track how all those nodes are connected together. So hopefully this is going to be a big improvement over trying to derive those big gradient expressions on paper. Here's another example of running in a computational graph. Here, this should look something like a logistic classifier if you kind of or care about these equations. But the details of exactly what the functions are computing for the purpose of this lecture are somewhat irrelevant. We just care about computing gradients in arbitrarily complex functions. But here on the left, we're showing we've got a function that takes 5 inputs. Our 5 inputs are w0, x0, w1, x1, w2. And now in the forward pass, we're going to compute this inner product between these first two elements of the weight and the first two elements of the x. And then we're going to compute this bias term to add w2. And then we're going to compute some kind of a e to the minus something in this computational graph. And here, the computation will proceed much as we saw in the previous example. In the forward pass, we'll compute the outputs of the graph by evaluating the forward function for each of these nodes. And this will end up computing this final scalar output value on the right. And then during the backward pass, we'll iteratively multiply the upstream gradient by the local gradient at each node in the graph to compute the downstream gradients. So we'll always start with this base case. Base case of derivative of output with respect to itself is always 1. Next, we'll look at this 1 over x. We know that the local gradient of 1 over x is minus 1 over x squared, which gives us the local gradient. We can multiply these to get the downstream gradient. We can step through again. We know that adding a constant has local gradient of 1, so that we can easily pass those gradients backward. We can compute the local gradient of this exponential function, which is trivial, so that just lets us easily compute downstream gradient. And this kind of like process sort of steps backward, 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 one node at a time, where at each point we're just computing these local gradients and then multiplying the upstream and local gradients. But what's really interesting about this particular computational graph is that there's multiple ways in which we could have thought to structure this computation. In this graph, as I've written it out in terms of very basic, very primitive, very fundamental arithmetic operators of addition and multiplication, exponentiation, division, adding a constant, I've kind of broken down this computation into its barest fundamental pieces of arithmetic primitives. And as you kind of noticed by looking at this graph, breaking everything down into the barest arithmetic primitives at every graph ends up a little bit tedious. And sometimes we actually have our freedom to define for ourselves what the types of primitive operations we want to use in our graph. So in this example, so here we've kind of broken everything down into the basic primitives, but we also have the freedom to define arbitrary new types of nodes that can internally compute more complicated functions. An example of why this might be useful is that this little chunk of the graph that I've outlined in blue independently computes this so-called sigmoid function that is 1 over 1 plus e to the minus its argument. This sigmoid function shows up all the time in machine learning. We've seen it in the context of this shows up for a binary cross entropy when you're doing a two-class logistic regression. This also shows up in many other contexts. And what's kind of nice is that we have the freedom as the designers of this little graph language to pick primitive graph elements that will be useful or easy to compute in the backpropagation process. And in particular, we can choose primitive functions to assign to nodes in the graph such that the local gradients become easy to compute. And this turns out to be the case for the sigmoid function. So the sigmoid function, if you kind of work through some math on paper, you can see that the sigmoid, I don't want to work through the details of this expression here, but if you work through on paper computing the derivative of the sigmoid function with respect to its input, you can see that the local gradient of the sigmoid function actually has a very simple functional form. That the local gradient of the sigmoid function is simply equal to the output of the sigmoid function multiplied by 1 minus the output of the sigmoid function. What this means is that we can very easily compute the local gradient of this entire blue chunk of the graph without storing this whole intermediate chunk of the graph. And this is an example of ourselves as the graph designers cleverly choosing the primitives that we want to use in our graph language in such a way that will make it easy or more efficient to compute the derivatives during the backwards pass. So this is definitely something you should consider doing. And now if we were to imagine kind of an aggregate, so you could imagine an equivalent version of this graph which collapsed this whole blue box onto a single node that would then receive the upstream gradient on the right and now compute the local gradient using this expression we've derived at the bottom of the slide, and then immediately return the downstream gradient on the left, kind of skipping over all of that intermediate computation inside the box. So this idea of defining more complex primitives to use in our graphs is something that we'll use quite a lot in general in order to make our computational graphs either be more efficient or have more semantic meaning. Another thing we can start to notice when we look at these computational graphs is that there's some patterns that become apparent when you look at the patterns of how information propagates during the forward pass and then during the backward pass. What you can kind of think of, what I sometimes think about this is like a little circuit that during the forward pass, we're kind of flowing information forward from the input to the output, and then during the backward pass, we're kind of flowing information backward from the loss through each of these intermediate nodes backwards to the original parameters of the model for which we wanted to compute gradients. And when you have this kind of circuit interpretation of these computational graphs, you start to notice some patterns about how gradient flow, some dualities between how information flows during the forward and backward passes. So the simplest example of this is that this add gate or add function acts as a gradient distributor during the backward pass. So if we have a little function which locally computes the output as the sum of its two inputs, maybe here 7 is 3 plus 4, then during the backward pass, we know that, as we saw in the first example of our very first computational graph, recall that the derivative of x plus y with respect to x is 1, and the derivative of x plus y with respect to y is also 1. So the local gradients of both of the inputs are 1. So that means the downstream gradients for both of the inputs are both equal to the upstream gradient. And this would generalize to a sum with an arbitrary number of terms. What this means is that during the backward pass, when you have a sum node, during the backward pass, that sum node is going to distribute and copy those gradients from the upstream into the downstream, which is kind of a nice intuition about what's happening when you have addition inside of your model. Now, kind of dual to the sum node is the copy node. This is kind of a trivial node that during its input maybe receives some input and then has two output values that are both equal to identical copies of the input. This seems like maybe a stupid operation at first glance. Why would you ever introduce such an operation in your graph? Well, you might want to do this if you want to use one term of your model in multiple places downstream in the graph. For example, you might imagine in a regularization setting, we actually want to use each of our weight matrices in two ways in our model. We want to use the weight matrix 1 to compute scores in kind of the main branch of the model. And second, we need to use the weight matrix to compute our regularization term, like L2 or L1 regularization. So in order to use our weight matrix in two downstream parts in the graph, we might imagine inserting a copy node somewhere in the graph that now makes two identical copies of the weight matrix that now can be used in different parts of the graph. And the important bit is that even when we've produced these two copies, because they may have been used in different ways, we might end up computing different gradients with respect to the two copies. And now, so then during the backward pass, the upstream gradients that the copy node receives might be different for the two outputs that it's produced. But now, during the backward pass, we simply need to sum those two gradients, which shows that kind of the add gate and the copy gate are somehow dual. That the add gate forward operation is kind of the same as the copy gate backward operation and vice versa. So these two operations are somehow dual to each other. Another kind of funny thing that's going on is a multiplication gate. You can think of this as a kind of swap multiplier, because you know that the derivative of xy with respect to x is y, and derivative of xy with respect to y is x, which means that the local gradient is, for one of the inputs, is the other input, and the local gradient for the second input is the first input, which means that when we compute the downstream gradient is equal to the upstream gradient times the other input. And this has kind of a funny implication if you think about, now if you have a multiplication inside your model, it's going to mix the gradients all up in some kind of a funny way. And because during the backward pass, the backward pass of a multiplication gate also involves multiplication, you can see that you're going to end up with some very large products in the backward pass. This you can imagine might be a problem in certain types of models. Another one that you might see a lot is a max gate. So here the max gate is going to take two scalar inputs and return the maximum of the two inputs. And here, what does that function look like? That looks kind of like a ReLU function a little bit. So then you can imagine that for the input that was indeed the maximum, the local gradient was 1. And for the input which was not the maximum, the local gradient was 0. So this has the interpretation that during the backward pass, a max gate acts as a gradient router, that it's going to take the upstream gradient and route that upstream gradient towards the one input that happens to be the max, and the downstream gradients of all the other inputs that were not the max are all going to be set to 0. So then you can imagine that if we had a model that was taking a max of like many things, then during the backward pass, we'll end up with a gradient that is mostly 0. So you can imagine maybe that's a problem for getting good gradient flow throughout the entire model. So maybe we might not prefer to use max for that reason. So these are all obviously sort of trivial mathematical expressions, but it's sort of interesting to think about how these trivial derivatives of scalar functions actually can have non-trivial consequences for the way in which gradients tend to flow through these giant neural network models. So now that we've hopefully gotten a bit of intuition about what is backpropagation and how can it help us automate the process of computing gradients in big models, I think it's helpful for you guys to talk about how you actually might implement this stuff in code. Because that's something you have to do in your homework, so hopefully you will get good at that. Well, I think I think about at least two major ways in which I tend to think about implementing backpropagation. The first is what I call a flat implementation of backpropagation. So here the idea is we're going to write a single Python function that computes the entire computational graph. Maybe this Python function is computing a linear classifier, and it inputs a mini batch of data and your weights, and then it computes the loss on that mini batch of data. Sound familiar from homework 2, hopefully, those of you who have looked at it? And now you're asked to have a single function that is going to both compute the loss and compute the derivative of the loss with respect to each of those weight matrices. Well, one thing you can do is kind of go to town on paper and kind of like you do your derivatives, and it's a mess, and hopefully you'll eventually pass the gradient check. But you can try to structure this computation in a much simpler way that I think makes writing this backward pass code actually very simple in this case. So here we're gonna, as an example, we're gonna have this little computational graph on the left, which is the sigmoid example from a couple slides ago. So we're gonna input our two weights W0, W1, our two inputs X0, X1, and our bias term W2. The forward pass of our code is simply gonna apply this, add and multiply these things and compute our loss L. And now the backward pass code is gonna be right after the forward pass code. And the trick is that the backward pass code is going to look like a reversed version of the forward pass code. What do I mean by that? Well, you can see that the very first thing we do in the backward pass is compute this trivial base case of grad of output with respect to itself is 1. You probably should actually omit this line in your actual implementation, but I wanted to be super pedagogical here. But here you can see that this first line in the backward pass code corresponds to this really rightmost thing in the computational graph. Now, this second line in the backward pass code corresponds to backpropagating through this sigmoid function. And you can see that the backpropagation line to the sigmoid function corresponds to the last line of the forward pass. And here what we notice is that in the forward pass, the sigmoid function was taking as input S3 and returning as output L. And now the corresponding line in the bit of backward implementation kind of inverts that around a little bit. Here, the backward pass takes as input grad L and produces as output grad S3. So you can see that there's a one-to-one correspondence between this line in the forward pass and this line in the backward pass. And now the inputs and the outputs are somehow swapped between these two corresponding lines. Then this correspondence continues. That in the second to last line in our forward, we wanted to add these two things, S2 and W2. Now because this was an operation with two inputs, it gives rise to two lines in the output in the corresponding backward code. And again, we can see that we have this intuition of the add gate as a gradient distributor. So you can see that we're simply distributing or copying the gradient to the two inputs in these two lines. A similar thing happens with this third to last line in the forward. And now very similar things happen in this fourth to last line in the forward. But again, now we've got a multiplication gate. So we've got this interpretation of this local gradient add multiply swapper. And then finally, we've got this final output that does the same thing. It's also a multiplication. And now this is kind of amazing, right? We actually wrote a correct implementation of backpropagation without writing down any math. We didn't write down any equations on paper. All we had to do was think about we wrote the code for our forward pass, and then we just transformed in our mind the code that we wrote in the forward pass. We just transformed it to generate the code for the backward pass. This is the way that you should actually go about doing homework too, if you have not completed those assignments yet. And this will make your life much, much easier when it comes to computing gradients. It turns out that once you get enough practice with this, you almost never need to do math on paper in order to write gradient code. You simply look at the code that you wrote for the forward pass, and you just invert it using all these little local rules that you pick up over time. So this idea of flat backpropagation that you implement by inverting the code from your forward pass is something that you should do in assignment 2. So for example, for the SVM, you could imagine that we might compute the scores, might compute the margins, might compute the data loss. And now in the backward pass, you'll just do all of those things in reverse. Except the exact operation that occurs during each line in the backward pass will be this local computation, which is the multiplication of the upstream gradient and the local gradient in order to compute the downstream gradient. And you can see that you can do this for an SVM, you can do this for a 2-layer neural network. Interesting that I chose these examples. So I would highly recommend that you become familiar with this way of sort of transforming your forward pass code in order to compute the backward pass. But of course, this kind of mechanism of transforming this way of doing flat backpropagation is really useful when you just need to write a gradient function end to end. But it kind of fails this modularity test. Because here, with this version of flat backpropagation, if we change the model or we change the activation function, we change the loss function, we change the regularizer, we're going to have to rewrite our code. And that's going to be a little bit painful and a little bit annoying. So there's a second way, which is like the more industrial strength way to implement backpropagation, which is to use a more modular API. And this fits very much with this idea that we saw of local computation around nodes. So here, with this modular implementation of backpropagation, we will typically define some kind of computational graph object and this computational graph object will be able to do forward and backward passes throughout the entire graph by doing some topological sort operation on all of the nodes of the graph, and then calling these little forward operations on each node during a forward pass, and then calling the corresponding backwards operations on each node during the backward pass. Now, this piece of code that I'm showing you here is just pseudocode. Like, this is not actually real code. It could have typos, I don't know. But this one actually is real code. In PyTorch, you can actually define your own functions using this API. So by subclassing torch.autograd.function, now you are defining your own little computational node, a little object, which represents a node in a computational graph. And now you can see that this object defines two functions, forward and backward. Forward takes 3 inputs. The interesting ones are x and y, which correspond to the input values that this node will receive during the forward pass. And these will be specified as torch tensors. In this case, we're just working with scalars, so this would be torch scalars in this case. We also receive this context object that we can use to stash arbitrary bits of information that we want to remember for the backward pass. So you can see that in the forward pass, we're simply defining this output z equals x plus y and returning z. These are all operations on torch tensors that you got familiar with in the first 2 assignments. And now in the backward pass, we write this function called backward that receives that same context object from the forward pass. So we can use that context object to pop off any stuff that we needed to remember from the forward pass in order to compute our derivatives. In this case, we need to remember x and y. And now we also receive grad z, which is this upstream gradient also stored in a torch tensor. And now internally, we locally compute this product of the local gradient and the upstream gradient to compute our downstream gradients, which are the derivatives of the 2 inputs. And we simply return those. And now this is like real torch code that you could use to implement your own scalar sum of two scalars. So that's actually already implemented in Torch, so I don't recommend you actually use this implementation. But if for some reason you did want to define your own arbitrary function in Torch and define the forward and backward passes of your new operation, this is how you can actually do it in PyTorch. And now if you look into, deep in the guts of the PyTorch code base, basically what is PyTorch is this Autograd engine and a ton of these little functions that define paired forward and backward functions. So here I'm showing you just like there's a lot of files in here, and this is somewhere on the PyTorch GitHub repo, and if we zoom into one of these files, this is actually one of many implementations of sigmoid that's actually deep inside the guts of PyTorch somewhere. So you can see that here, we're actually defining the forward pass of sigmoid, using deep in C++ or C or something, deep in the guts of PyTorch, that's computing the forward pass of the sigmoid layer. Unfortunately, it calls into this other function, which is defined somewhere else. It's a bit of spaghetti code if you actually ever looked at the back end of PyTorch. But we can ignore that. And now there's the second paired function, which is thnn sigmoid update grad input, which computes the backward pass. And it does some boilerplate, unpack tensors and do some checking of input. This is a real industrial strength code base. But now there's this critical line where you can see that it actually is, right here is where PyTorch is actually computing the backward pass of the sigmoid layer, deep inside C, nested inside some macros and some crazy stuff going on. But basically what is PyTorch is these paired forward and backward functions that can then be chained together into these big computational graphs. So basically, up to this point, we've really only talked about the notion of using backpropagation and computational graphs using scalars, which is really easy and intuitive if you kind of remember everything from single variable calculus. But in practice, we often want to work with vector-valued functions, or functions that operate on vectors or matrices or tensors of arbitrary dimension. So we also need to think about what does it mean to do backpropagation in computational graphs with vector or tensor valued, with vector or tensor values as well. Well, here we need to recap a little bit some of these different flavors of multivariable derivatives. Well, you remember the normal single variable derivative, given a function that, given a scalar input and a scalar output, the derivative of the output with respect to the input tells us this local linear approximation. If we change the input by a little bit, then how much does the output change? We've got this familiar gradient operation, and a gradient is the type of derivative that is appropriate where our function takes a vector as an input and produces a scalar as an output. And then this gradient, dy dx in this case, is then a vector of the same size as the input, where each element of the vector of the gradient vector says how much does the output change if the corresponding element of the input changes by a little bit. So it's a vector of these sort of classical single-valued derivatives. And now the generalization is a function that inputs a vector and outputs a vector, possibly of a different dimension. And here, these things all have different names, but they're all basically the same idea. They're all derivatives. And this one is called a Jacobian. Now, the Jacobian is a matrix where it has a number of elements, which is n times m, if those are the dimensions of our input and our output. And the idea of the Jacobian is that it says, for each element of the input and for each element of the output, how much does changing one of the elements of the input affect that element of the output? And now, because we've got n input elements and m output elements, we need n times m scalar values in order to represent all those possible effects of inputs on all the outputs. Okay, so then now suppose we got the same picture that's kind of, right, we know that we don't really need to think about graphs as a whole. We only need to think about how does backpropagation work for one node at a time. So then what does it mean to do backpropagation in this vector valued case, kind of zooming in on one node again? Well, here we've got now our little function f is inputting two vector values. X is now a vector of dimension dx, y is now a vector with dy elements, and we're producing a vector output z with dz elements. And now this is our forward pass. It's very easy. Things are happening. Eventually we'll receive this gradient up from upstream. Now this upstream gradient, now in this vector valued case, it's important to remember that the loss we compute is always a scalar, no matter whether we're working with vectors or tensors or whatever. This final loss we compute at the end of the graph is always going to be a scalar. And now this upstream gradient that we receive is going to be the gradient of the derivative of the loss with respect to our outputs. So that's going to tell us for each of the outputs from this node, if we were to change each of our outputs by a little bit, how much would they affect the loss way down to the right of the graph at the very end of our computation. And now the local gradients in this case become these Jacobian matrices. Because in this case now our function is a vector valued function that takes two vectors as input, produces one vector as output. So now our local derivatives become these Jacobian matrices that again tell us for each output element from this node, how much is it affected by changing each input element of this node. And now the downstream gradients that we want to produce are always going to be the derivative of the loss with respect to the inputs. And now derivative of loss with respect to a vector input is now again going to be a vector of the same size as the inputs. So the downstream gradient that we produce for x is going to be dl dx, which will be a vector of the same size as x. The downstream gradient we produce for y will be dl dy, which is a vector of the same size as y. And now to actually produce these downstream gradients, we know we need to multiply the local and upstream gradients, but now that we're working with vectors, it's not a scalar multiplication anymore. Now this becomes a matrix vector product, where the local gradient is now this Jacobian matrix, and the upstream gradient is this gradient vector. The downstream gradient is a gradient vector, and the way that we produce this downstream gradient is a matrix vector multiply between the upstream gradient vector and the local Jacobian matrix, in such a way that the shapes work out. So if you're ever confused about this, I always just recommend writing out the shapes of all of your things, and hopefully that will help you clarify what's going on. Now, as a concrete example of doing backpropagation with vectors, we can imagine what this looks like for the ReLU function. So for the ReLU function, remember that it's an element-wise max of where we clip everything below at 0. So given an example input vector x of 1, minus 2, 3, minus 1, applying the ReLU function to this vector would sort of replace all the negative values by 0. So our output y would be the vector 1, 0, 3, 0. And now this ReLU function, this kind of vector-valued ReLU function is one little computational node embedded somewhere in our graph. And now eventually will be returned this upstream gradient, which tells us how much would that final loss change if any of our little outputs from our ReLU function changed. And these could be arbitrary values, positive or negative. We don't know or care how they're computed. They're just handed to us by the differentiation engine. And now this Jacobian matrix tells us for each input of our local function, how does each output of our local function change? And what we can start to notice here is that the Jacobian matrix of this element-wise ReLU function has some special structure. So because this is an element-wise function, we know that the first output of the function depends only on the first input, and the second output depends only on the second input. In particular, the first input does not affect the second output or the third output or the fourth output. Each input only affects its corresponding output in the same position in the vector. What does that structure look like in a Jacobian matrix? That means that the Jacobian matrix is diagonal. that all of the because the off-diagonal elements of the Jacobian tell us maybe how does element I of the input affect element j of the output, where I and j are not equal. So for this element-wise function, all those off-diagonal elements of the Jacobian are 0. And now for the on-diagonal elements, that becomes this scalar-valued derivative, which tells us how much does the ReLU change as a function of changing the input. So then for the positive valued inputs, they'll have a local gradient of 1 on the diagonal, and for the negative inputs, they'll have a local gradient, or local derivative of 0 on the diagonal. And then by working through this, it lets us form this full Jacobian matrix for the input. And now, remember, to compute the downstream gradient, we need to compute this matrix vector multiply between the upstream gradient vector and the local Jacobian matrix. So you can compute that thing offline, and then we can produce this downstream gradient vector that will be passed to the other nodes that we're feeding into us as input. And now we start to realize something interesting, is that this is actually, in this case for this ReLU function, we saw that the Jacobian matrix was sparse, that the Jacobian matrix had a lot of zeros in it. And this is actually the common case for most of the functions that we use in deep learning. In general, most of the local Jacobian matrices that we use are going to be very, very, very sparse. So in practice, we will almost never explicitly form this Jacobian matrix. And we will almost never explicitly perform this matrix vector multiply between the Jacobian and the upstream gradient. So you can imagine that for this ReLU example, it's maybe fine to form the Jacobian for a vector of 4 inputs. But what if our inputs was like a mini batch of 128 elements, and each of all those elements was a vector of like 4,096 dimensions? Now this Jacobian matrix would be like super, super gigantic and super, super sparse. Like only the diagonal would be non-zero. So in general, actually explicitly forming those matrices would be super wasteful, and explicitly performing that multiplication with a general matrix multiply function would be super inefficient. So really, the big trick in Backprop is figuring out a way to express these Jacobian vector multiplies in an efficient, implicit way. And for the example of ReLU, this is trivial, because we know that ReLU has this structure where the output, where the diagonal entries are either 1 or 0. So this means that for the ReLU, we can compute this downstream gradient by either passing on the upstream gradient or killing the upstream gradient and clipping it to 0, depending on the sign of the corresponding value of the input. And the way that you should think about this expression is that this is a very efficient implementation of an implicit multiplication between this large sparse local Jacobian and this upstream gradient vector. Is this clear? So then now this has been talking about vectors, but of course we need to work with tensors of rank greater than 1. We need to work with matrices and 3-dimensional tensors and 4-dimensional tensors and like arbitrary things. Now the picture is very much the same. So to understand how to work with backpropagation with tensors of with matrices or tensors of arbitrary dimensions, we have very much the same picture. That now we have our local function. I deleted the f accidentally, that inputs 2 values x and y. In this case, they're going to be matrices. X will be a matrix of size dx by mx. Y will be a matrix of size dy by my, and the output will also be a matrix. Now, remember, the loss is still a scalar, and all of the gradients of the loss with respect to something will always be a tensor of the same shape as something, which will tell us how does the final downstream loss change as we vary each of the independent elements of that input of that tensor. So then when we finally receive this upstream gradient, it will be a matrix now of size dz by mz, which will tell us, again, how if we change any of the elements of our output, how much will that loss change. And now these local Jacobian matrices get very interesting in this sort of tensor case. Because recall, these Jacobian matrices need to be able to tell us, for each scalar element of the input, how much does each scalar element of the output change. Which means that this Jacobian matrix is now a kind of like generalized matrix type of thing. So the number of elements of these local Jacobian matrices is maybe like dx times mx times dz times mz for this local Jacobian matrix between x and z. And I often think about, in this case, grouping the dimensions of the Jacobian matrix, where we have one group of dimensions corresponding to the shape of the input, and one group of dimensions corresponding to the shape of the output. And in that way, we get this Jacobian matrix is this very high rank tensor that has it's kind of the product of the sizes of the input and the output. And now the downstream gradient proceeds in much the same way, that the downstream gradients are then going to be, again, tensors of the same shape as the inputs, giving us these downstream gradients. And in order to compute them, we still need to do a kind of matrix vector multiply between these local Jacobians and these upstream gradients. The problem is that now they're not quite vectors and they're not quite matrices. So we need to think of these as a kind of generalized form of a matrix product, or right? Where now the local Jacobian matrix, you can imagine kind of flattening these two groups of dimensions corresponding to the input and the output that would actually give us a literal matrix. And you can imagine flattening the output to be a high-dimensional vector and flattening the input to be a high-dimensional vector. And then that kind of results that then you can, after flattening, actually literally perform a matrix vector multiply and get these downstream gradients. But I don't know about you, but whenever I think about these like higher dimensional implicit Jacobian matrix vector multiplies between like super high dimensional tensors, like my brain ends up exploding. And it becomes very difficult to actually think about how to write down an expression for implicitly computing this like giant sparse matrix vector multiply thing. Like, it's a mess. So to help you out, I'm going to work through a strategy that you can use to help you implement these types of operations without actually thinking about really high-dimensional, high-rank tensors. So for that, we're going to work through a concrete example of deriving the backpropagation expression for the case of matrix multiplication. And this is going to be super pedagogical, but this will be a general strategy that you can apply for deriving these backpropagation operations for kind of arbitrary functions of tensors and crazy shapes. So here we're doing a matrix vector multiplication between an input x, which is a matrix of size n by d, and I've written out a concrete example of a matrix of size 2 by 3. We have a weight matrix of size d by m, and again we have a 3 by 4 concrete example. Now our little computational node is going to do matrix multiplication and produce this output y that hopefully I did the math right. And then during the backward pass, we're going to receive this upstream gradient from somewhere out in the graph that's going to tell us how much do each element of y affect that final loss L. And again, these can be arbitrary values. And our goal is to compute this downstream gradient, which is how much does each of our inputs affect the loss. I think you got that by this point, hopefully. And now, if you imagine actually what are the sizes of these Jacobians, they're going to be pretty big. So like n by d times n by m. And here on the slide, I've shown you kind of these simple small examples, but for a real neural network, we might have like n is like 64, and d is and m might be like 4096. So if we multiply those out, each of those Jacobians is going to be like 256 gigabytes of memory in FP32. And the biggest GPU you can buy on the market today, I think, has like 48 gigabytes of memory. So it's like, this is clearly not going to work to explicitly form these Jacobians. And that's like pretty small neural network anyway. But so basically, the whole trick here is to find a way to express this computation without explicitly forming the Jacobian and without explicitly doing that matrix vector multiply. So you need to find a way to do that implicitly. And the way that you can think about doing this is kind of element-wise on the input. So what you can think about doing is think about one element of the input. Think about x11. And now we want to think about what is going to happen just thinking about x11. And now we can compute a slice of the local gradient. This local gradient was this like really big thing of the full shape of the input times the full shape of the output. But this slice of the local gradient, what I mean by that is the derivative of the output, the matrix output y with respect to the single scalar input element x11. And now because this is the derivative of a matrix by a scalar, it's going to be an object of the same shape as that matrix, telling us how much does each element of the output y get affected by that one scalar element of the input x. And now, to make matters further, then we can think, what is this first element of this local gradient slice? This first element of this local gradient slice tells us how much is y11 affected by x11. Well, we know that matrix multiplication, in order to compute that value y11, what we computed during matrix multiplication was an inner product between the first row of x and the first column of w. So then we can write out this expression on the bottom here for how we actually computed y11. And then we can imagine computing the derivative of y11 with respect to x11. And we can see that all of these other terms fall away, and the only part that matters is this first term of x11 times w11, and we know how to take derivatives of a product of two scalars. So we know that that local gradient, that piece of the slice of the local gradient is now just equal to W11. So in this case, it's going to be 3. Now we can repeat this process for the second element of this local gradient slice. And now the story is very much the same. This second piece of the local gradient slice says, then this says, how much does this blue element of the input affect this purple element in the output? And again, this purple element in the output was an inner product between the first row of x and now the second column of y. So then again, it looks like this inner product. And again, all but one term vanishes, and we see that the gradient, we just pick out this value of W11. So the second element of the slice is 2. So it's just going to copy over one of those elements of the weight matrix. And I'm not going to bore you with the next two, but basically at this point you should see the pattern, that this first row of the local gradient slice is just copying over this first row of the weight matrix W. And now what about the second row of the local gradient slice? Well, the second row of the local gradient slice is going to ask the question, how much does this, again, we're still working on one element of the input, how much does the blue element of the input affect the purple element of the output? Well, remember now the purple element of the output is computed by an inner product between the second row of x and the first column of y, but what you'll notice is that it doesn't involve that x11 term at all. So here the local gradient is 0 for this little chunk of the local gradient slice. And now you can expect that this pattern will repeat for all of the other elements in the second row of the local gradient slice. So then now, through that excessively verbose explanation, we've finally computed this local gradient slice. And now we're ready to compute the one element of the downstream gradient. So we can finally now compute this blue element of the downstream gradient by computing an inner product between this local gradient slice and the full upstream gradient. And now this will tell us how much does this one element of the input affect the final loss at the very end of the thing. So then you can see that this local gradient slice now ends up being this inner product between the between this local gradient slice and the full upstream gradient. But because the local gradient slice was copying one row of the weight matrix and the rest of it was zeros, what this means is that this element of the input of the downstream gradient is really an inner product between the first row of the weight matrix W and the first row of the upstream gradient dl dy. So now, at this point, we can kind of throw away this local gradient slice and forget about it. And we can realize that we only needed to look at that one row of the weight matrix and the one row of the upstream gradient to compute the downstream gradient. And now we could imagine doing the same thing for another element of the input. And we could go through this whole same song and dance to compute this local gradient slice by kind of reasoning one element at a time. And now you can see that if we were to pick now the local gradient slice for x2, 3, that is this bottom right element of the input x, now our local gradient slice has this same kind of structure. That this local gradient slice is now copying one of the rows from the weight matrix, and it is 0 everywhere else. So then, but when we take this inner product, we see that this other element of the downstream gradient is again an inner product between one of the rows of the weight matrix and one of the rows of the upstream gradient. And now you could kind of work through this with some complicated indexing expressions on paper, but it ends up that you kind of get this general expression that now you can kind of jump and see that for any individual element of the downstream gradient, it ends up being an inner product between one of the rows of the weight matrix and one of the rows of the upstream gradient. And once you realize this relationship, you don't actually have to form that upstream gradient, that local gradient slice at all. And we can compute all of these inner products between the rows of the weight matrix and the rows of the upstream gradient, compute them all at once using the single matrix product between dl dy, the upstream gradient, and W transpose, the transpose of the weight matrix. And people get confused about this sometimes, and people look at this expression and think that we are somehow forming the Jacobian here. And we are not forming the Jacobian here. What this expression is doing is that by taking this matrix product between the upstream gradient and the weight matrix, this is actually an implicit matrix vector multiplication between this very large, high-dimensional, sparse Jacobian and the upstream gradient. Even though it looks like a matrix product, this is actually not explicitly the Jacobian times the upstream gradient. This is somehow an efficient way to compute that sparse product. And by the way, a really easy mnemonic to remember this expression is that it's the only way the shapes can work out. So you know that when you compute a product of two things, then the derivative should involve the upstream gradient, and because product is a gradient swapper, it should involve the other input value. So then in order to compute the downstream gradient for x, we know it has to involve the upstream gradient, and we know it has to involve w, and then there's only one way to multiply them that results in shapes of the same shape as x. So that's the pro tip, is this is an actual trick to remember matrix multiplication, just match up the shapes. And it turns out that the exact same heuristic also works for the other input, right? So if we want to compute now dl dw, again, we know it has to involve the upstream gradient, we know it has to involve the other input, and there's only one way to match up this product in a way that makes the shapes work out. So this is a super easy way to remember how to compute these things. So another view of backpropagation is that we have this long chain of functions. We've got like f1 and f2 and f3 and f4, and we eventually produce this scalar loss L. And now by the multivariate chain rule, we know we can expand out this gradient expression and write dl dx0 as this product of all of these Jacobian matrices, which are the intermediate Jacobian matrices, and this final gradient matrix, gradient vector on the very far right. And we also know that matrix vector products are all associative. So we, in principle, could choose to perform this multiplication of all these Jacobian matrices and this final vector in any grouping or in any grouping that makes sense. And what's happening in backpropagation is that we've chosen the particular grouping of computing these products right to left. And what's really nice about computing these products right to left is that we never have to do any matrix-matrix multiplication. Because if we compute these products right to left, then we only ever end up having to do matrix vector multiplication, which is much more efficient. But this whole thing hinges on, right, this is a very nice algorithm, but for that to work out, it means that we always need to be computing a final scalar loss at the very end. And this algorithm only works for computing the derivatives of that final scalar loss with respect to everything else in the graph. And there might be other situations where you might want to do something else. What if, for instance, you want to compute the derivative of a scalar input and get the derivatives of everything in the graph with respect to a single scalar input? Now that corresponds to a different version. Oh, and by the way, this backpropagation algorithm, because of this method of multiplying because of this interpretation of multiplying the Jacobian matrices in this right to left way, this is sometimes referred to as reverse mode automatic differentiation. It's a fancy sounding name. And from the name, you know if you're explicitly calling it out reverse mode, then there should be forward mode as well. And it turns out there is. So the forward mode automatic differentiation is for this slightly other case, where we have a scalar input value, and now we want to compute the derivative of that scalar input value with respect to everything else in the graph. And then you can see that if we kind of think about it in this viewpoint of vectors and Jacobians, then again, we can multiply these things in any way. But if we perform the multiplication left to right, then we again get kind of only matrix vector multiplies. And by the way, you might ask, why would we want to do this? In machine learning, we always want to compute we always have a loss at the end, and we want to compute derivatives with respect to that loss in order to do gradient descent. Well, I know it's hard to believe, but there's actually more to the world than machine learning. And sometimes it's useful to have computer systems that can automatically compute gradients for us when we're doing things that are not minimizing a loss function. So an example here might be we have some physical simulation. And this input A is maybe like a scalar parameter giving the gravity or the friction or something of that physical simulation. And now we want to compute how much would all of the outputs of this simulation change had one of those scalar inputs, so controlling the gravity or the friction or something changed. So this kind of idea of automatic differentiation is generally useful far beyond machine learning. It's really useful anytime you want to compute derivatives for any kind of scientific computing application. But the downside is that forward mode differentiation is not implemented by PyTorch and TensorFlow and all the other big frameworks. So unfortunately, even though it has these really cool applications and maybe scientific computing and whatnot, it's not super easy to use because they don't implement forward mode reverse automatic differentiation. And they've had issues about this open up on GitHub like the day TensorFlow released, but it still hasn't been merged in. But thankfully, there's a clever algebraic trick you can actually do to compute forward mode gradients actually using two backpropagation operations. And there's a link to that here. It's a super clever piece of algebra that I'd really encourage you to check out if you ever happen to find yourself wanting to compute forward mode gradients in a deep learning framework. Now, another kind of really useful trick that we can use once we have this viewpoint of backpropagation, kind of multiplying tensors and Jacobians and vectors and whatnot, is we can actually use this same backpropagation algorithm to compute not only gradients, but also higher order derivatives as well. So as an example here, we're showing a very amended computational graph where we have an input x, so it's a vector of size d1 that goes through f1 to produce another intermediate vector of size d1. Then we go through f2 to produce a scalar loss. And now, what if, so far we've always talked about first derivatives. We always talked about gradients and Jacobians and normal derivatives. But in this case, the second derivative of the loss with respect to the input x0 is now a matrix that tells us all of these second derivatives, right? Well, that's if we were to kind of like, if we were to change x0 by a little bit, like change one element of x1 by a little bit and change another element of x1 by a little bit simultaneously, then kind of how much is the loss changing? Or equivalently, if we were to change one of the elements of x1, then how fast would the gradient change is another way to think about this Jacobian matrix. Or sorry, this Hessian matrix. See, these things are easy to get mixed up, but be very careful. Hessian matrix is second derivative, Jacobian matrix is first derivative. Jacobian matrix is vector in, vector out. Hessian matrix is vector in, scalar out. Simple. But it turns out sometimes you might want to compute elements in your computational graph that are a function of this Hessian matrix. So an example would be a Hessian vector multiply. Say we have this Hessian matrix, so we want to compute the Hessian as a matrix, so we have a vector that we want to compute this Hessian vector product. Why would you ever want to do this? It turns out there's reasons. For instance, there's an iterative algorithm to approximate the singular values of a matrix using kind of these matrix vector products. So, for example, you could, if you wanted to compute some kind of second order information about the singular values of the optimization landscape, then you might want to compute Hessian vector products to approximate those singular values. And it turns out, through a bit of clever algebraic transform, derivatives are linear and gradients are linear functions are amazing. So we can actually rewrite this second derivative of this matrix vector product as the derivative of the inner product between the gradient and the vector. And I'm pretty sure this works out, right? But of course, this is only true if the vector is a constant and doesn't depend on x0. If it does, then you get another cross term. But now we can do something very clever in our computational graph. So we can extend our computational graph with these backpropagation functions. So now what we can think about is extending our computational graph. So after we compute the loss, then we use this function f2 prime to compute the gradient of the loss with respect to x1. We can use f1 prime to compute the gradient of the loss with respect to x0. These are these little backward functions that were implemented by the backward pass of the little f gates. And then we can implement this dot product with f and think about that as another node in the computational graph. And then this final output is going to be the inner product between the gradient, dl dx0, and the vector, and this vector that we've chosen v. And now, in order to compute the derivative of that thing with respect to x0, we just need to backpropagate through this graph. So what this means, this is like kind of magical the first time I saw it. But basically what this means is that if all of your backward pass operations, when you implement your little gradient nodes, if the backward pass is itself implemented using differentiable primitive operations, then you get all these higher order gradients for free. And you can use backpropagation through these computational graphs to compute functions of second derivatives. And by the way, you can similarly do higher order derivative things as well. You can imagine computing a third derivative is now going to be a three-dimensional tensor. Then you can compute bilinear forms on top of this third derivative, which is like kind of hard to think about. But you could imagine extending this type of operation in order to compute derivatives of arbitrarily high values using the same simple backpropagation algorithm. And unlike forward mode automatic differentiation, this actually is implemented in all of the major deep learning frameworks like TensorFlow and PyTorch. So you can do some crazy shenanigans and write down loss functions that involve gradients. Why would you ever want to do that? It turns out people actually do want to do that sometimes. So an example here that from this paper called Improved Training of Wasserstein-Gans, they actually write a regularization term that depends on the gradient of the loss with respect to the weight matrix. So here it has the interpretation that we want to write down a regularization term that penalizes the magnitude of the gradient. which means that we kind of want to find weight matrices that result in well-conditioned optimization landscapes, which is a pretty cool idea. And then you can actually implement this kind of crazy regularizer by using this idea of higher order differentiation through these computational graphs. So then kind of the summary of what we saw today is that we could represent these very complex functions using this computational graph abstraction that is hopefully going to be a lot nicer than working out things on paper, where then it's going to have this forward pass that computes gradients and this forward pass that computes values, backward pass that computes gradients. And then you don't even really need to think about the full graph most of the time. You only need to kind of zoom in and think about this local picture of little computational graph nodes that compute outputs and then multiply the local gradients to compute downstream gradients. And then hopefully the really important part for your homework that's due in a week will be this idea of implementing backpropagation using this kind of flat backprop way, where your backprop code looks like an inverted version of your forward pass code. And then we also talked about this more modularized API, that lets you be more modular and swap things out in a better way. And actually on assignment 3, we'll implement a more modular API for other types of neural networks. So now, kind of at this point in the class, we've seen linear classifiers, we've seen neural networks, we've seen how to compute gradients in these things, but we've had a big problem, which is that both of these networks had this operation where we kind of stretch out the pixels of the input image and take our input image and stretch it out into a vector, which basically destroys the spatial information of the image. That seems like a bad thing, and we'll fix that in next lecture when we talk about convolutional neural networks.